You step up to your front door, slide a piece of brass into the slot, and turn your wrist. You feel the heavy, solid clunk of the deadbolt sliding back, and the door swings open. The satisfying, weighty resistance of that motion creates a specific psychological impression. It feels as though you are manually using torque to grind thick metal components past one another. Yet the sheer weight of that solid oak door and the heavy steel bolt securing it are currently held in place by internal mechanisms that weigh less than a paperclip. Looking closer, we have to account for what occurs in the dark, tightly enclosed space of the lock cylinder during that fraction of a second. Unlocking a door is a deception of scale. This microscopic sequence of events hides behind the appearance of a crude act of physical strength. To see how it works, we shrink down into the brass housing of the lock, a dark, tightly packed cylindrical environment. This cross-section reveals the primary obstacle, tiny vertical pins resting at randomized heights, blocking rotation. The horizontal shear line separates the outer housing from the inner cylinder. Because pins bridge this gap, twisting causes them to bite into the shear line, binding the mechanism. As long as a single pin bridges that boundary, the cylinder remains an immovable object, capable of snapping the metal before it yields to force. Look at the physical key on its own. Cut along the top edge is a jagged profile of steep peaks and deep valleys. These peaks and valleys function as a topographical map, encoding specific spatial data into the geometry of the metal. Watch as the tip of the key smoothly glides into the narrow keyway, sliding directly beneath the pins. Your forward motion pushes those angled slopes against the pins,